Section 7 in Chapter 17 talks about the Diels-Alder reaction. This is a hugely important reaction to synthesize cyclohexene derivatives in one fell swoop. In this reaction, a conjugated diene is react with something that's called the dienophile. The dienophile can oftentimes have these substituents attached to it. So this reaction proceeds like so. The arrows I'm showing here look a lot like a benzene resonance, and what is formed here is a cyclohexene with a double bond located on the left as drawn, and your X group will be here, okay? So you need to have a conjugated diene that can adopt the S-cis conformation. Okay, and what's found is that electron donating groups on the diene work really well. Okay, your dienophile is an alkene or an alkyne. And it generally has electron withdrawing groups as an X. Okay. Electron withdrawing groups are, generally speaking, carbon-oxygen pi bonds, things like that. So when you look at the generalized reaction, what they first tried was reacting butadiene and ethylene at very high reaction temperatures, and they got a 20% yield of the cyclohexene, okay? But they then extended this to other reactions that had electron withdrawing groups attached to their dienophile. So this right here is X, that's the electron withdrawing group, okay? And when these two react here, under the right reaction time and temperature and conditions, you can form the product here. The book states in 100% yield, okay? So that's a dramatic improvement, and you do not need very, very high reaction conditions. So the groups that can be attached to your dienophile can be aldehyde, as I mentioned. They could be various ketones. You can have esters. You can have carboxylic acids. And you can have nitriles, okay? So these are all suitable dienophiles that make the reaction happen much faster and at milder reaction conditions, okay? So rule 1 is that you want your dienophile to have electron withdrawing groups for a faster reaction, and your diene, it can be ordinary butadiene, but you can also have electron donating groups, okay? Rule 2 can succinctly be stated: cis forms cis, trans forms trans. And I think I should use a new page to explain this. So if you have butadiene and you're going to be reacting with this guy here, we say this is a cis alkene because the two substituents are on the same side. Okay, so cis here refers to the stereochemistry of the alkene. We sometimes say it's Z, all right? When this reacts, you'll form the cyclohexene, and you'll form a cyclohexene where the two cyano groups here, or the two nitriles, are also cis, okay? Cis here does not mean there's a double bond, that the two groups are on the same side as the double bond. It means that the two groups are on the same side as the ring, okay? So the cis here refers to the ring system. If so, cis forms cis in this case. If you have a trans alkene that's serving as your dienophile, okay, so here we have a trans or an E alkene. This guy here will also form a cyclohexene product. And you'll get the two stereoisomers here. You'll get a racemic mixture of the trans, okay? Now the reason why you only form one molecule of cis up on top is because that's a mesostructure. Two wedges and two dashes are identical because of the plane of symmetry there in the molecule, okay? Now keep in mind that your dienophile could be an alkyne. So here's our dienophile, and you can see here how it's an alkyne. So there's no cis or trans with an alkyne, and when these pi bonding electrons scoot around, you're going to form a carbon-carbon bond between those two dotted lines and a carbon-carbon bond between those two dotted lines. And if you pay attention carefully to the positions of the pi bonds, you will see that we have a pi bond on the left. That's our cyclohexene. This is our template. But on the right, the triple bond gets converted to a double bond, and then our two ester groups remain unreacted here. Okay, so you form a product that looks like that. Okay, so keep that in mind when you're looking at things. We have a problem here on page 801, just to get warmed up. So this is problem 14. Okay, let's do this problem together now. Okay, problem 14 says predict the products, okay, for each of the reactions. And there's A through I here, so there's quite a few. So here we need to pay attention to the geometry of the alkene. It's cis. So when these two come together, you form the cyclohexene. The double bond will be on the left, as you can see by the curved arrows for the reaction mechanism. And we want to put two esters now that are cis. And again, it doesn't matter if we choose wedge or dash, because this is a mesostructure. It's achiral, and either of those two representations would be fine. This molecule here on the right is a cis dicarboxylic acid. So we can also show the curved arrow reaction mechanisms here. We can show our cyclohexene and our two carboxylic acid groups. You can write COOH, CO2H, or draw it out as a Lewis structure. I will draw it out as a Lewis structure here. And I'm just writing the C there just to overemphasize things. Now, this molecule here is a trans, okay? Sometimes it might be helpful to highlight the carbon-carbon pi bond, you know, circle or identify the two groups. So we're gonna have a ketone here and a ketone here. And so when these two come together, you're going to form a cyclohexene. On the top carbon, we're going to have our ketone. On the bottom carbon, we're going to have our ketone. And of course, we're going to form the enantiomer. So like the book does, I'll just write plus En, which they sometimes do. Okay. The next problems, we have this reaction here. So this is going to form, once again, a cyclohexene, but since we're going from a triple bond, that gets converted to a double bond, and then we're going to have a ketone on carbon 1 and a ketone on carbon 2. This molecule is sufficiently arranged so that you can see the two coming together. You will form a cyclohexene there on the left. And this guy is a ring, so we need to put a fused ring here. We can use wedges and draw our anhydride functional group there, like so. Okay, so those are supposed to be wedges, kind of hard to see here on the drawing. Okay, and once again, because this molecule is meso, is achiral, you could draw that as a dashed. Both dashes would be fine as well. Okay. Here as well, if it's problematic to see, you can draw it in a vertical fashion here so that you can see how the molecule comes together, and that's going to form cyclohexene as usual on the left, and the triple bond gets converted to a double bond, and then we'll have our two nitriles here as shown. Okay. This next problem here, this carbon and this carbon and this carbon and this carbon are going to become attached, and we have a whole ring system here. So what we're going to form is a cis ring system, and oftentimes when you have these cis fused ring systems, you can sometimes draw it like this, where you draw the H's coming up. Okay, so instead of drawing something like this, which looks kind of awkward, we choose to draw it with that representation where we just draw the H's. Okay, so here we want to draw these two carbons and these two carbons connected, so that's going to be our cyclohexene. You're always going to form a six-membered ring with a double bond in it. We have a triple bond here, so that gets converted to an alkene, and we have a carboxylic acid here. Okay. In this molecule, you're going to connect these two carbons together. You're going to form the cyclohexene, and then you have this very large R group, but that's fine. You just add it in there. It's going to be your molecule, okay? So don't get confused by larger groups hanging off. It's just part of organic chemistry. That could be a simple R group, a methyl-ethyl, or in this case, a cyclohexyl group, okay? So that's the basics of the Diels-Alder reaction. Now, the thing to keep in mind is that when this reaction takes place, these two carbons and these two carbons have to be in sufficient close proximity to react. We call that the S-cis conformation. And this reaction is quite slow because, remember again, that the equilibrium favors the S-trans conformation, which is unreactive because those two carbons are too far apart. So one way to speed up these reactions is to use something like this, cyclopentadiene, and if you react that with ethylene, that'll give you a bridge bicyclic system that looks something like this. And this is locked in the S-cis conformation. So the two alkenes are in a ring, so it's locked. So it has to react by a very quick reaction, okay? So this is going to be slow, this is going to be faster, because you're favoring that conformation that's reactive. Let me highlight for you where this six-membered ring comes from. You have two carbons, 4 total carbons there in yellow. Okay, those are the 4 carbons. And then you have this alkene, which is another 2 carbons, and that's the other 2 carbons, okay? So this bond right here and this bond right here are the 2 new bonds that are formed in this cycloaddition reaction, okay? So it's hard to see the bridge bicyclic systems, okay? So that means that things like this will react because the alkene is arranged in an S-cis orientation. But if you have things like this, that will not react because the alkene is positioned in S-trans configuration, it can't rotate around when you have it locked in a ring, okay? The third rule for the Diels-Alder reaction is something called the Endo Rule, okay? And this is most often seen with bridge bicyclic systems. So if you have a bridge bicyclic system, you have two positions. You have endo, which is underneath the ring away from the bridge. Okay, that's the bridge kind of like thing. And endo is underneath, okay? Or inside. And this is called exo. So it turns out that things like to be endo when there's a Diels-Alder reaction. And okay, so let's take a look at this figure. What we see is a transition state between cyclopentadiene, that 5-member ring on top, and that's reacting with a dienophile that has the alkene that's very activated from the aldehyde. And so what I'm trying to do is draw the alkene with those two aldehydes tucked under the ring. And when there's bond formation between these dotted purple carbons here in the top figure from Klein's organic chemistry textbook, the aldehyde is going to position itself underneath the ring. We call that endo. So whenever you have a bridge bicyclic ring forming from a cis dienophile, you want to draw those substituents on the endo side of the ring system. Now, if you have, so again, let's summarize what happens. If you have this and you have a cis dienophile, okay, you want to draw the, one way to figure out how to draw things is to draw your cyclopentadiene as though it was an envelope that with the flap sticking up. And then what you want to do is draw your cis dienophile here, and in 2 dimensions, okay? These two react top to bottom. They don't react side to side because the p orbitals are all coming in and out of the plane. But you want your envelope to go right on top of that dialdehyde there. And so that's going to form the product, okay? So let me use a different colored pen here. You're gonna form bonds here and bonds here, and it might help to make a molecular model from this. So that's going to form just what the textbook showed you. It's gonna form a nice 6-membered ring there, and you're gonna form the aldehyde down below, okay? So there's 2 things to note with this structure. One is that you're forming a cis adduct. That means that the 2 aldehydes are on the same side of the ring and they're both endo, okay? So kind of practice drawing this sort of thing and be able to draw that. Now, if you have a reaction where you have a trans, okay, dienophile, that's going to give you a bridge bicyclic system once again, okay, with your cyclo, hexene, your alkene in there. And we have 2 carbons here. Maybe I should highlight this in green. One of these is going to be endo. One is going to be exo, okay? The reason for that is because trans makes trans, okay? This is trans, and this ring system is trans. So we can't position both substituents endo. You only get the endo when you have one substituent or you have a cis configuration. Let me show you what it looks like when you have one substituent. When you have a cyclopentadiene reacting with acrylonitrile here, this will give you your typical bridge bicyclic ring system, okay? And you want to draw the cyano group endo, okay? So that summarizes the three situations you might encounter when you have a trans dienophile, when you have a cis dienophile, and when you have just an ordinary dienophile. The endo pops up when you have cyclic dienes, like this right here on the screen, Cyclopentadiene, okay? Let's practice this, problem 19 in the book. Okay, so here we have the molecules drawn out for us. And in class or in lab, when I have much greater time to spend with students, I would make models and explain this in greater detail. So I suggest reading the book carefully. This video does not replace the textbook. Here we have a cis dienophile. So remember, if we're starting with cyclopentadiene, there's the 4 carbons, and the 2 circled carbons are going to make this bridge bicyclic system. Okay, so there's my 6 carbons, and this bridge right here is created from that 1 carbon. And now I have those 2 CN, right, nitrile groups. So I want to place them in the endo position, and I point them away from the green dot. So that's all I need to do. I don't need to add hydrogens or anything. Well, I do need to show the double bond. Okay, do not forget the double bond. You're always going to form a cyclohexene. There's a 6-membered ring with a double bond hidden in there. In molecule B, we have a similar situation, but instead of a carbon, we have an oxygen right here, okay? So let's start by drawing our template. And make sure you put your double bond in there. So that's an oxygen on top instead of a carbon that's dotted green. And now remember, I have the trans, so it doesn't matter which one I choose. Draw one up and draw one down, okay? One's gonna be endo, one's gonna be exo, and you do form the enantiomer from that, okay? In molecule C, we just have 1 substituent, so we need to draw that endo. So for molecule C, we draw our template that comes from cyclopentadiene, okay? And then I want to draw an aldehyde endo, so I want to draw that down on the board. I can choose either of these carbons. I can choose the back carbon or the front carbon, okay? Let me copy this to a new page. Okay, so D, E, and F we want to work on. So here again, we have diene, and we have some weird stuff attached to it, but that's fine. Let's go ahead and draw in our template. Now, this guy here with the sulfur, we need to add some things, okay? So instead of a carbon, we have a sulfur on top, okay? We always form that cyclohexene, and we have 2 methoxy groups. Okay, we have these 2 methoxy groups, all right? Now on the other end of the molecule, we're going to incorporate 2 carboxylic acids. Since this is trans, we can't go wrong here. I'm gonna draw 1 going up, 1 going down, and I realized that I could have the other way. So that's the enantiomer. In molecule E, once again, we build out that template. We draw a cyclohexene, all right? And the cyclohexene is gonna have 2 methyl groups on the left, and then the bridge carbon here is just, you know, ordinary carbon. Now I have a mono substituted alkene, so that's my dienophile, and I wanna draw the CN group here going down, which is endo, okay? In F, we have a similar situation. We have 2 rings, so I urge you to try to do models of these, but what you're going to form from this guy here is, again, build your template here, okay? draw the alkene, and then what you're going to need to do is modify your template. So instead of a carbon, we have an oxygen, so I'll just put an oxygen there. Okay. And on the right, I have a ring with an anhydride, right? Two esters that are kind of bonded to one another. And that's going to be endo, so that's going to be underneath the ring. So I'm going to draw that crazy looking ring underneath. Okay, and I don't need to draw the hydrogens there, but it might help you to see things if you do draw them in, okay? So I'll draw them in, okay? That in a nutshell is a quick crash course on the Diels-Alder reaction. It's quite complicated, but the book has much greater detail, and you might need to review things at your own leisure. Thanks for watching.